There you go. But I will be talking about those subjects. I'd like to thank the organisers for giving me the opportunity to talk today. This is not entirely all my work. My job at Auburn University is plasma diagnostics, mainly for magnetic confined plasmas. But the work on uncertainties I'm presenting today is a collaborative work from several institutions. Stuart Locke, who is the local ADAS expert at Auburn University, and he's now been working sort of with the ADAS group and on collisional radiative modeling for magnetically confined plasmas for the best part of a decade. On astrophysical plasmas, I've been working with Mike Witthoff and Tim Coleman. Mike Witthoff was the main developer of some of the Monte Carlo codes that I'm going to show today. And these guys have their own several databases. Tim Coleman has the X-star photoionization database, and Mike Witthoff wrote the UAB, which is a general database for all collisional processes, excitation, ionization. And locally here we have the ATAMP crew, we have Adam Foster and Randall, and we all collectively are interested in putting uncertainties on atomic data, but not as isolated cases, but rather how these uncertainties will interact with each other towards a plasma diagnostic, like, for example, a line ratio. Now, like many people in the audience, I maintain and develop a suite of collisional codes. Oleg and Chris develop and maintain their set of codes as well. But today, rather than sort of give a survey of what uncertainties uncertainties there is in light species, medium species, up to relativistic and heavy species such as tungsten, I'm going to use as my example helium-like oxygen, very simple case, but I'm going to consider all the collisional processes that go into that and how we're assigning uncertainty to it, both from a sort of first step approach, which we call the baseline, and another approach which we call the method sensitivity, but I'll get to that.
Connor, I have two slight comments.
Okay.
I like Adam Foster and Randall Smith very much.
Oh, I've made a mistake.
ITAMP. I'm willing to give them honorary. That was one. I mean, from where you are, of course, the resolution is not high enough to see. But the other one, we're not meeting in Boston.
It's a resolution problem.
Well, it's good to see I've been just uncertainty in the first slide.
There's an uncertainty implication.
So there's one thing we can reduce in terms of uncertainty and sensitivity is we should go out and evangelize about how important this is. There's some people that get it and are coming around to the point of view. There's a recent paper by Manuel Bautista, but in terms of getting long-term funding and having a real go at this, we need to impress upon the funding agencies to supply many years of funding, so we can implement this within both the magnetically confined fusion plasmas as well as astrophysical ones. This is a good case. There's a range of people that are completely ambivalent when you put in a grant proposal. They go, yeah, we understand that might be useful, but it's not at the top of our priority list. And then at the other extreme, there's very blunt people saying, I don't think this has any impact on astrophysics at all. Maybe Randall has had a similar encounter with some of these referees that I have. But that's one thing we can do. We can't be, in terms of sensitivity, we can't be sensitive. We have to say it's needed, and we have to, in many ways, remove the uncertainty that it's needed. Okay, so first comment is preaching to the choir. It's this has been asked for many decades that we put on a meaningful uncertainty or collisional calculations. the group that I've discussed have categorized this problem into two groups. The first we call the baseline uncertainty, and the second method we call method sensitivity. So the baseline uncertainty we would say as the first attempt calculation. We would go into the literature that's currently available and see what the range of values is. That would give us an indication of, there's variation of 40% amongst these different calculations. Or another way to look upon it is a calculation that you can do quickly. Maybe do a plane wave Born or a distorted wave calculation and vary that calculation by 20 or 30%. But that's just to give us an indication of the parameter space. The next method is method sensitivity. So this is taking the sophisticated methods like convergent close coupling, the R matrix method, the time-dependent methods, and then running thousands of these calculations, varying the structure each time. So we're going to take 1,000 different structure calculations, take those orbitals, and then run them for excitation, ionization, and dielectric recombination as our first model. So I like this method because we don't come with any preconceived ideas. We're going to run a statistical model of 1,000 calculations. We're not going to assume a Gaussian distribution or any distribution, and we're not going to impose upon a 10% error bar on a dipole light transition. We're just going to come to that with the results we get from our 1,000 R matrix calculations. My third point is, in the line of work that I'm doing, the goal is not to provide a cross-section in isolation. It is to use it as a temperature diagnostic or an impurity influx from a tokamak. We want to use the data. In that regard, it's not how one collisional process acts, like excitation, but how excitation, ionization, and dielectric recombination interact with each other. So this is just to make the last point a little bit stronger. The dotted line is an ADAS calculation, but it's actually an RMPS calculation for the ionization of neutral lithium. So in neutral lithium, the ground state configuration is 1s squared 2s, where the 2s is almost embarrassment, only bound by 5 eV. And the dotted line can be done by any of the methods that people in the room use, but that would just be the ionization for the 2s. However, what we find in a plasma experiment is that it's not just the ground state ionization, the total ionization is from the excited states as well. So you could think of that as a two-step process, excitation and then ionization out of the excited state. And that is the solid black line there. So now you're already muddying the waters because instead of a direct ionization, you've got excitation and ionization. And the black line actually includes ionization of the very high end shell. Now, we can't carry out the sophisticated methods up to n equals 100. So that can be a mixture of, say, an RMPS calculation for 2 up to 5. Then we have to fill in some of the excited states by maybe a distorted wave calculation from 5 to 10. And then some sort of semi-empirical fit for the higher end shell as well. So now you're really muddying the waters because the error on different methods all contribute to give this result, and it seems to be verified by experiment. So again, we can't consider processes in isolation. So this is a more detailed rundown of the two methods that I've said. So at the top are the strengths of the two methods going down to the negative. So baseline is uncertainty quantified as the difference between two theoretical approaches. Say an excitation from distorted wave or plane wave Born, convergent close coupling, and say an R matrix calculation. And this is good because, again, you don't come with a preconceived idea of a particular error. You just take the difference you get between the values that are in the literature right now. The benefits of it quickly provides a generous uncertainty on an atomic data set. Do we need a more refined calculation for the future? If these simple models work, don't do the more refined calculation. However, the negativities are it may not reflect the type of constrained uncertainty derived from a more elaborate calculation, more accurate structure, a non-perturbative method. And of course, all these calculations are done at various institutes across the world, so there's no consensus on what is the right atomic structure even before you carry out the calculation. Now, the uncertainty within the sensitivity study is because you're essentially controlling the calculation. It's done at one institution. It's used with the same codes, the same atomic structure, the same collisional code. And because you start from the same atomic structure for, say, dielectric recombination, ionization, or excitation, you've removed the uncertainty due to the atomic structure. However, the most negative thing is it's more time and resource intensive. Now, Klaus made the point earlier this morning is to do these calculations, we must apply for time on computer centers throughout the US. And this requires a full grant proposal to do so. And it's a very hard sell that I'm going to ask for 65 million hours at, say, Oak Ridge National Laboratory, and then after 3 months you say, well, I ran the same calculation 100 times just to verify I got the same result. So you're going to have to change the mindset of people that this is required. And this is back to what I said in the second slide. However, once we've got all these different methods, we can then feed the rates into Monte Carlo collisional radiative modeling, varying the A values, the dielectric recombination, radiative recombination, ionization, excitation, de-excitation, and get uncertainties in emissivities, line ratios, temperature, and density diagnostics. This, we've already sort of put this into our previous meeting in Korea, and if you want the details of that, it's in Fusion and Technology, volume 63, and that will give you in greater detail all the choices that we've made. So, I'm going to use helium-like oxygen as an example, and then discuss each of the three methods and how we're going to put uncertainties. So I'm going to be talking about this from a baseline perspective, how we're going to do the first cut of the calculation, and how we're going to assign sensitivities or uncertainties. So these are well-known astrophysical line diagnostics. This is a helium-like system. I've put on the labels, astrophysical labels, and on the diagram I've put on the sort of atomic physics labels as well. So we're coming from a 1s squared ground state. You've got the resonance line, it's a singlet P, 1s2p, and then we have spin and forbidden line, the triple S, 1s, 2s. And these lines are used as temperature diagnostics in many astrophysical plasmas for oxygen all the way up to iron-like cases and beyond. So, of course, what regime should we be focusing on? At really low temperatures or lower densities, then we can get away with the coronal approximation, where we essentially have an excitation rate up and an A value down. On the y-axis there, we have the population of an excited state over the ground state population. Then as we increase electron density, we get into the more interesting collisional radiative regime. So therefore, there's a lot of processes going on here. We can have excitation up to a level, cascades down. We can have ionization from that level, dielectric recombination into that level. All of these have to have uncertainty and an error associated with them. And then finally, if we go up in density high enough, we get into the local thermal equilibrium, and then essentially the atomic physics is almost washed out. So uncertainties are a function of temperature and density. So just to reiterate, aim is for baseline uncertainty data is to generate a range of values that should encompass most of the currently available data in the databases. So ADAS, ADB. We're looking for generous error bars. This is going to be our first cut. It's going to see what lines are sensitive, what transitions, with a simple approximation so we quickly know what we want to focus on. But we also want the uncertainties to have the sort of correct temperature, maybe end shell behavior. So we can say that this line may be temperature or density diagnostic are sensitive. So if we go to the literature, and I did a quick scan of the literature for excitation of oxygen 6+, and there's several calculations. So the red line is one done by the Auburn group, and this is the intermediate coupling field transformation. So it gives you level resolved excitation. This one here, I think, is the 1 to 2 transitions. So this is the singlet S to the triple S. There are other R matrix calculations, one with the fully relativistic dark code by Agrawal. There's the flexible atomic code, distorted wave code, blue circles, and we also have autostructure now, the Bragg-Ploy distorted wave. Now, this is one way to get uncertainty. The distorted wave case, although it can be run with isolated resonance approximation, we're trying to create a generous error bar here for the baseline study. So the R matrix calculation is going to have the resonances. When we integrate underneath the curve, you're going to get a higher rate for the R matrix because it includes the resonance. The distorted wave will not. But we will see that this will be a function of temperature. So the top graph here is our effective collision strengths from each of these calculations. The red line at the bottom, and this is not to abuse the distorted wave method. It obviously it can include resonances, but we're trying to just generate a generous uncertainty. We can see that percentage error at low temperatures can be as far as 80%. As you do the higher energies, the area under the curve washes out the contribution from the resonances, and the agreement gets better. So our baseline uncertainty data is for the excitation is the difference between the R matrix and the distorted wave epsilons, and that is for a spin forbidden transition. Of course, there's no real such uncertainties for the dipole like transitions because the background cross section is so strong. Again, it washes out the contribution from the resonances almost completely. So again, here's the 1s squared to 1s 2p dipole light transition. And here's our percentage error as a function of temperature. And of course, not surprisingly, it's good agreement. So that's how we would sort of handle excitation within a baseline approximation. One way that we consider now doing uncertainties in ionization cross sections, at least for a highly ionized case such as this, but 6 times ionized, is to, in a distorted wave approximation, you can build a continuum wave function both in the potential of the incoming electron or of the residual ion. It's called like post and prior, mid-check or younger potentials, depending on where you're from. And this is our attempt to find, what would be a realistic and meaningful uncertainty on the ionization cross-section. Of course, if we went to more neutral stages, then the ionization cross-section would differ between sophisticated methods and the distorted wave. But as a first cut, this is going to give us a range of uncertainty for ionization. So, in the handout before we came to the meeting, there was some discussion on resonance position. Resonance position has a strong effect on dielectric recombination cross-sections, essentially because they have no background. It's literally resonance on nothing. So we were trying to come up with a quick method to again, put a meaningful uncertainty on the DR. And one way we would do this would be, we would run a default calculation where we take the atomic structure we get and the DR cross-section, and then one in which we move or shift our target thresholds to the NIST core excited energies. Of course, this is probably not a particularly good example because the structure for 6 times ionized species is fairly accurate to begin with. However, in other systems, it can have a large effect. So this is an experimental calculation carried out by Mike Fogel, and we're comparing sort of theory and experiment, and we can see that at higher energies, the agreement between theory and experiment is quite good. However, when we get down to the low energies, especially the ones close to the ground state threshold there, we're not getting the resonances positions correctly. And this can have a very dramatic effect on the rate coefficient. So let me blow up that energy region close to the ground state. Yeah. So again, here's the rate coefficient, and as a function of temperature, and we see that this large bump in the rate coefficient comes from a single resonances that is 60 millielectron volts above the ground state. How accurately can we get that single resonance in theory? Well, not to 60 millielectron volts, or it's very, very hard to get within 60 millielectron volts. So that's going to be the dominant concern when we're considering dielectric recombination rate coefficients from more complex species. Now, there's a slight caveat that I'm going to add here, that with Nigel Battle and myself, I think last year considered tungsten 20 plus, so there's a change of gear from helium-like oxygen up to tungsten 20 plus. Tungsten 20 plus in atomic physics is the worst case scenario. It's F8 ground state. So that's 192 levels just within the ground state configuration. Okay? However, it's going to have a Rydberg sequence going to every one of those 191 excited states. It becomes less important there where an individual resonance is because there's just simply a forest of them. Its more completeness will give you an accurate calculation rather than the position of an individual resonance. So, in fact, there's certain people in Queen's Belfast, Gleb, that are using sort of, so they refer to it as chaotic Hamiltonians. They're saying that we don't know the positions of these resonances. We're just going to come up with a statistical argument based on the density of the states rather than the position of an individual resonance. Okay, so if we go back to our helium-like case, these are the sort of uncertainties or sensitivities we would expect from the difference between our theoretical models and Mike Fogel's experiment. I should say hybrid rate from experiment is they do the low shells up to n of 69, and then they're topping up with the theoretical resonances from n equals 69 up to 1,000, so that's why it's hybrid. But this shouldn't affect the low temperature rate coefficient. So that's what we've done, and this is what we'd like to do. In the terms of our matrix calculations now, Mike Whittle, Stuart and myself have now written the Perl script. And in its simplest terms, it is once we have a structure, we can hit the return key and we will get an effective collision strength. Because we want to do thousands of these calculations and we can't do that by hand. So we need some way to automate this. And we now have got to the point where our matrix calculations, both for excitation and ionization, are reduced to one partial wave because every partial wave is being done concurrently, sometimes with many processors per partial wave. So essentially all we're doing is running one partial wave for excitation and ionization calculations, of course doing every partial wave on a different core, and then this is sped up our matrix calculations to the point where we can do these thousands or at least hundreds of calculations. It also helps if we have access to machines like Python at Oak Ridge, and then you can really crank up and get through these calculations a lot quicker. You can see here that if you go up to 128,000, you can get 0.4 of a petaflop. So that's 4 times 10 to the 14 operations. Okay. So what we want to do is build up a distribution from these thousand calculations, and we need to speed up, say, a hydrogen or helium-like calculation to the point where we're doing one every couple of minutes.
Connor, it's not clear to me what's changing from one atomic structure calculation to the other. Sorry. Looking at this distribution.
Okay, so this is almost a lengthy conversation, but one way would be to do it. Say, I'm looking at a helium-like iron case. I run a Hartree-Fock calculation for the hydrogen-like case, a Hartree-Fock calculation for the lithium-like case. This gives me my orbital eigenenergies for the 1s, maybe up to the 4f, right? Then I have a Thomas Fermi potential I can have a Thomas Fermi orbital for the 1s orbital, but I vary it so it's always between the orbital eigenenergies of the neighboring stage. That would put a tight constraint on the inner orbitals, but as you go up, it would expand outwards. I'm not saying that's a perfect scheme, but that's one way that you would do it.
So that's for the helium-like stage.
Yeah, but you could move that along, that argument. And that's how you would realistically put constraints that are meaningful. Inner orbitals not varied much. As you go to the outer orbitals, there'd be a larger variation. So this requires a very, very careful bookkeeping. So we use what is known as the ADF04 file within ADAS. We want to have, if you can think of these 1,000 calculations as 1,000 shots of an experiment. It's one way to look at it. So every one of these files has your structure, your energy levels, the term, J value. Here we have a range of temperatures in Kelvin. We have every transition, we have the A value, and we have effective collision strengths as a function of temperature. And we have this thing called, this is the infinite energy point, or the beta and the null point. So this is a complete representation of one of those calculations. So the nice thing about this is we can take this format, and in the same way that we have effective collision strengths here, we can replace that by the error. So the file would be exactly the same format, but now we would have an error file for a particular calculation. But this is the sort of, again, the comment that Klaus was making earlier on. We can do this for simple systems like the hydrogen, the helium, the lithium. If we came to tungsten 3+ that has a ground state of 5D3, then you're not going to be running one of these every couple of minutes. They're going to be tens of thousands, well, not tens of thousands, but 12,000 plus a couple channels. These are going to take a long time to run. It's going to take a day or so. But again, this is R matrix calculation versus a distorted wave. The large difference between the distorted wave and the R matrix is because in the ground state complex here, you have 19 levels that are very, very closely packed, and there's strong coupling between the ground state and the excited 18 levels, whereas at the distorted wave won't have that. So we have a recommended data set plus uncertainty data set. For the baseline data, we can have a Gaussian distribution and provide a sort of standard deviation for the Gaussian. We then do a Monte Carlo set of collision-related calculations, typically about 1 million. And those are post-processed to create line ratios. So this is what we've done in our procedure for the baseline. Our most likely result is the red line. This compares with the Smith paper. And there's our generous error bars, but you can see that our error bar is a function of electron density. So again, hammering home the point, errors is a function of temperature and density. For the baseline, we're unsure of what sort of distribution function that we would use. We've tried the Gaussian, however, that doesn't necessarily fit well because a cross-section has a hard starting point, and then it's essentially unbounded in terms of energy higher up. So we're finding that this is more physically relevant to do what is known as a log normal distribution, which has that shape. However, we're still at a very, very initial stage here. We're really just playing with distribution functions, trying to find one that is as physically meaningful as possible. We tried Gaussian because it was easy to implement. So we think our method for generating baseline certainty is reasonable. However, we'd like to extend this to do the method sensitivity studies, which we think are going to be a more rigorous. You don't come with preconceived ideas of a particular 10% for this type of transition, 20%. You take what you get from the 1,000 calculations.